Okay, so today is probably the hardest day because the material that we're going to cover today is just so much different than the things that we've been doing in the past. Like up until this point, pretty much everything that we've covered has been chapter 2, just in radians. Today is just like definitely a different idea where we're covering something called angular velocity and a manipulation of formulas, and it definitely does a lot more of like a physical application to understand why radians and why this idea of having things on a unit circle is really important. So first though, like we have kind of two parts to this lesson. The first part is talking about domain. So we've talked about domain the very first chapter. Remember, domain are things that you can plug into your function. So for example, stuff like this has some limited domain because we can't plug in all values for x. So like this domain, remember, was 0 to infinity. You could only plug in positive numbers for that. So that's what we're looking at, is like what kind of numbers can we plug in to our functions, and we're going to talk about domain of all of our trig functions today. So let's just think about our trig functions again as some intercepted arc. So like if this is along our unit circle, like that, and we have some theta measurement, some angle measurement. This part here is that intercepted arc of S. This is our theta, which these things correspond, right? And this side we're going to label here on our triangle as A, and this side we'll label as B. Now we know on our unit circle that our radius here is 1. And then we can say that our sine value is really this opposite side, or as we labeled, we're going to label it here as A. And we're going to write it both ways to kind of see if there's a difference. So likewise, we can always also represent the cosine as my x-coordinate, which is my b value on my unit circle. And then my tangent, which is my opposite over my adjacent, would be, or sine over cosine, is a over b. Now cosecant, which is the reciprocal of sine, is going to be 1 over a, and likewise the reciprocal of cosine, which is 1 over b for secant, and then cotangent is b over a. And remember, like a is really sine, so I'm just going to write it this way so we can kind of keep that in the back of our mind. Oops, cosine. And then this a value again would be our sine value. This would be like sine over cosine, and then cosine over sine. Now again, when we're talking about things that we can plug into our function, we want to make sure that we have our rules of domain kind of covered. And if you think about back to chapter 1, we had 2 rules of domain that we were worried about. One was this instance where we had like the square root. We can't take the square root of a negative. The other issue that we had was something like this, where our denominator couldn't be 0. Like I couldn't plug in x equals 0 to this function because it would give a domain error. Like tried it in your calculator and you would get an error message. So that's what's happening here, is that since we have a denominator, we can't have the denominator cannot be equal to 0. Which means that we're going to have to restrict our functions a little bit. So I can't plug in anything for cosecant because I have a denominator problem. However, cosine and sine, both of those are dealing with like any ratio, any value on our unit circle, and really kind of any values for our theta, because this is again some angle. Any value of a degree measurement I can plug in. Like I don't have any issues with a domain because I don't have a denominator, I don't have a square root, so I'm not getting anything that's really an issue here. So my domain for both of these is negative infinity to infinity, meaning I can plug in any angle that I want. I can plug in negative angles, I can plug in positive angles, I can plug in 0, I can evaluate all those things. However, for the rest of our 4 trig functions, we are dealing with some sort of fraction, and that means that we're going to have some issues with our domain. I can't actually evaluate everywhere here because this might be 0. And that's what we're going to look at, is like where sine is 0 and where cosine is 0, and that'll allow us to come up with our restrictions for our domain. Now, if you notice, cosecant and cotangent, these two, have the same issues for our denominator. We both have a in the denominator, or in other words, we both have sine in the denominator. So for our domain for cosecant, we want to figure out where does sine of s equal 0. Because if we can figure out where sine of s, or where a sine of our theta value, if we can figure out where that happens on our unit circle, then we can exclude those values into our in our domain. Okay, so picturing our unit circle here, sine is our y value, so here we are. So at this coordinate point, I'm at 1, 0, which here's our sine, so we know that it happens at 0 degrees, 0 radians, and then it also happens over here at 180 degrees, or pi, and then it happens again at 2 pi. And I could keep going around and finding those coterminal angles. Like if I do another 180 degree rotation or another pi rotation, I'd end up here at 3 pi and 4 pi and 5 pi and 6 pi. So as I'm coming up with all these values, I'm noticing kind of the same idea, or the same pattern, that it's really any multiple of pi. So instead of writing out all of these into infinity, and we could also have like negative pi and negative 2 pi, negative 3 pi, we're just going to write k pi, where k is an integer. So a whole number could be positive or negative. So for our domain, we want to include everything except those values. So what that means is that if I take out my calculator, and just want to make sure I'm in rating mode. All right, so I want to exclude those values that give a domain error. So if I want to like not have any of these things, for example, like if I try to plug in cosecant of pi, which would be 1 over sine of pi, my calculator will tell me that I have an error, I'm dividing by 0. Same thing with 2 pi. Same thing with 3 pi. So the only values that will happen though are those pi, 2 pi, 1 pi, 2 pi, 3 pi, 4 pi, etc., k pi until infinity, where k is an integer. So I want to exclude it. Everything else is fine except for those values, because that's the only time where our denominator is equal to 0. It's the only time that we're going to get an error in our calculator. So cotangent, since it's dealing with the same denominator as cosecant, it has the same domain. Like the only values that you can't plug in are k pi, where k is an integer. And I'll tell you that all these domains are something that you need to know for your test on Friday. Okay, and you could always like try to figure it out. Like it doesn't mean that you have to memorize them, but if you can kind of derive it again, like okay, knowing that this is 1 over sine, sine is equal to 0 at these places, so I have to exclude them. You might also, this would be a good explain problem, like why is the domain for cosecant restricted? Why do we have to exclude some values? The reason is that sine is in the denominator, and sine of s can't be 0 then, because we can't divide by 0. Same thing for tangent. We're going to do the same process. Now tangent and secant, if we notice, have the same denominator. They have b in their denominator, which is really cosine. So for these ones, we're going to do the same thing, but we're going to ask ourselves the question, where does, instead of sine, where does cosine equal 0? So thinking about my unit circle, here it is. Sine equals 0 at 0 and pi. Cosine equals 0 at the other coterminal angles that we have, the 90 degrees and 270. Which are in radians pi over 2 and 3 pi over 2. So we have values that would equal 0 are pi over 2, 3 pi over 2. If I add another coterminal angle here, I end up getting, well, if I do pi over 2 plus 2 pi, because that's how we find coterminals, we add or subtract 360, but 360 is 2 pi in a unit circle. So if I do pi over 2 plus 2 pi, 1/2 plus 2 is 5 over 2, so that'd be 5 pi over 2. If I add it again, I'll get 7 pi over 2 and 9 pi over 2 and 11 pi over 2 and so on. So what we're actually getting is a kind of a similar pattern here where we have like multiples of pi, and specifically in our case pi over 2. But it's not just pi over 2, because that would be like 1, 2, 3, 4 pi over 2 is really 2 pi. So our k that we have to have, k pi over 2, k has to be an odd integer. It's all our combinations and all of our patterns of odd integers of pi over 2. So 1, 3, 5, 7, 9, 11, or -1, -3, -5, -7, -9, -11, so on and so forth. So that's what our domain is. It's everything except k pi over 2, where k is odd integer. I'm going to run it into my space here. And same thing for secant, -infinity to infinity, except those values where k pi over 2, where k is odd integer. So like again, for example, if I wanted to test that, I could try secant, which is 1 over cosine, and I want to test like 3 pi over 2, and I would get this error, I divide by 0, so I want to make sure that that value, the 3 pi over 2, is not included in our domain. That's something that we can't plug in, so we have to exclude it. And those are the only values this entire, I mean, it's an infinite number of values, because I can go around my unit circle an infinite amount of times. I can find all those coterminal angles, but they're all in the same pattern. They all have like k pi over 2 and k is odd. So that's part 1, is deciding what our domain and our range, or sorry, our domain is for these values. We've already done our range, if you remember, in chapter 1 of cosecant and secant, and then tangent and cotangent and sine and cosine. So now we've like accomplished our domain too. So eventually we'll put both of those together and we'll look at domain and range of all those functions. So part 1. Part 2 is talking about velocity, and so this is where our physical application kind of takes place. Velocity is some rate of change. It's some movement around in some particular distance. It's the speed of how something is moving at any given time. There are 2 different types of velocity though. There's linear velocity, which is usually what we think about when we think of velocity. It's a speed along a line. It's a speed over time. Our units for regular velocity is some distance per unit time. So like centimeters per second, or meters per second, or miles per hour, or whatever it is. So we actually have a formula for that. Like we usually use distance equals rate times time, and this rate is really our velocity. So if I were going to solve for our v value, I would divide both sides by t, and I would get my equation for velocity, which is distance over time. And that should make sense, because that's what our units are, some distance over some time. Again, usually that's what we think about when we think of velocity, is like the speed that your car is moving. However, there's a different type of velocity, and this velocity is around an angle or around a circle. So it's called angular velocity. So I want you to imagine like you're in your car right now and you're driving, and then you keep the same speed, you keep the same like linear velocity, and then you turn your car. That turning your car, you'll notice that you have like this pull on you. It feels like you're actually speeding up. That's why like you could like tip over a little bit. So your linear velocity, like your actual speed of your movement, is remaining the same. Like if you even set it on cruise control, but your angular velocity is changing, because now you're going around a curve, which is different and affects you differently. So these are very different, because this one's going along some straight line and this is around a curve. So like for example, if I was, you could think about like the planets too. Say I'm like here along some orbit, and I'm going some like angular velocity, which means I'm going around my curve. So this would be me around my curve. At any given point, I can keep going over here, this would be my angular velocity. At any given point though, I have a linear velocity that's also associated with this particle or orbit or planet or whatever it is. So like right now, if I imagine like you're kind of tethered to this string that's kind of pulling you along in this momentum, like this orbit that we're actually looking at. If I cut the string at some point, then instead of going around the circle, you'd be going straight. So that would be what our linear velocity is. So at any given point, we can kind of draw this, what's called a tangent line, and this would be our v value. That would be going in like one straight way. So linear velocity is going in a line, but angular velocity is going in a curve. And this idea is not really, like, this is not something that I'll ever ask you to explain. I just want you to get a visual idea of when you are talking about linear velocity or when you're talking about angular velocity and the difference between those. Okay, so for linear velocity, instead of going around in like some distance, what you're really doing is you're having some angle that's changing. Like you might be going from 0 to 180 degrees in a set amount of time, and that would give you a speed. So for our linear velocity, we have the formula of theta over t. And again, like I said, theta is always in radians in this chapter because we're in a radian chapter. So make sure that when you're talking about this theta that it's always some pi. And so our units for angular velocity is always radians per unit time. The book explains that radians is what's called a pure unit, that it actually doesn't have a unit attached to it. It's just some change in, which kind of makes sense, but it's some change in angle. So when we end up doing like, because the rest of this section, we have to pay special attention to our units, and you might be a little confused about the radians per time and how we're going to manipulate that in a little way. But just remember that like linear velocity, our regular velocity is always like miles per hour, and angular velocity is always radians per second or radians per hour or whatever it ends up being. Okay, so these are two formulas that you need to know, or that you need to use, so you don't ever have to actually know these formulas. They'll be given on your test. The other one that we've already kind of talked about is the arc length formula, which is our radius times our theta. And the reason why this is important is because we're going to kind of talk about this linear velocity in an angular way too. So in a circle, as I'm moving around, moving around a circle, the distance that I travel, so if I'm talking about my linear velocity, the distance that I travel around my circle is actually represented with our arc length. Which means that I can make a substitution that our d value for our linear velocity is really our radius times our theta. Okay? Now I'm going to make that substitution in my formula here. So I'm going to replace d with r theta. And I'm going to write this a little bit differently. So I'm going to write this as a radius times theta over t. And the only reason I'm writing it that way is because this theta over t is something that we've already defined as our angular velocity. So this is another formula that we can use, a manipulation, kind of a combination of linear velocity and kind of going around our circle, is that our linear velocity is really our radius times our angular velocity too. So these four formulas will be given to you along with the area of a sector, and that's what you'll be given on your next test. And it's really like the rest of the section is just kind of a manipulation of these formulas. So if you're good at kind of like manipulating some things and getting to the answer by just like plugging in values to formulas, then you should be pretty good at this section. It just gets a little bit confusing on deciding what's what. Okay? Okay, so I'm going to write all these on the top of my paper so that I can reference them. So the first one was that our velocity is distance over time, but we also know that our velocity we just found was our radius times our angular velocity. Our angular velocity is some change in radians over time, and then our arc length is radius times that theta value. So we have 5 problems to look at. We're going to be solving for lots of different things. So our first one is looking for the angular velocity, so W. which we know is theta over t. So I'm always going to start with my formula, and then I'm going to write out like what my theta and what my t are like given in my problem. So 5 orbits. So an orbit is all the way around a circle. So one orbit is really 2 pi. So that means that 5 orbits is 2 pi times 5, or 10 pi. That's going to be my theta, is 10 pi, because that's my change in angle. And my t value is this 7 hours. So if I replace that in my formula here, because I have both my theta and my 7, I'd have 10 pi over 7, and this would be for my units. It's kind of important to have them. Again, angular velocity is some radians and then per unit time, and our unit time is hours. So it's really important that you have your units there, because our time might change, or we might have disagreeing units. So if you keep track of those, at least like the radians part, again, that's just attached to every angular velocity, but the per hour thing is actually important. So that one is pretty easy because we have both the things that we need. We just kind of substitute it into our angular velocity formula. You're going to do the same thing here. So we're finding the angular velocity, that like W, of an object that does half an orbit. Okay, well, half an orbit, if one orbit is 2 pi, then half an orbit is going to be half of 2 pi, which is just going to be pi. So that's going to be our theta value, is pi. Our time, again, is 3 minutes, or it's given to us. So for this one, again, it's pretty easy. We have our theta, we have our time, so all we really have to do is plug it into theta over t. Our theta is pi, our t value is 3, and this would be then radians per minute. Those are our units. So that would be our angular velocity. Both those were pretty straightforward because we're given all the information that we need. This next one's a little bit different because we're not given all the information that we need to find everything, but we can use the manipulation of a couple different formulas. So I always like to write down the information that I'm given and then see what it matches up to these formulas to see which ones I should use. So right now I have the radius, I have my angular velocity in radians per second. We're going to find the linear velocity and the distance traveled in 10 seconds. So my distance is unknown, my t is 10, and my linear velocity is also unknown. So I have two formulas for linear velocity. Given what we are given here, I don't know my distance, but I do know my time, but I don't know my linear velocity yet. But I do know my radius and I do know my angular velocity. To find my linear velocity, I'm going to use this formula because I already have both these things, both of these variables that I can just plug in. So I'm going to use this one here right now, where my radius is 10 and then my angular velocity is pi over 18. And I'll simplify that, so I'd get 10 pi over 18, which I can reduce down, divide everything by 2 to 5 pi over 9. And my units on this, remember, this is in radians per second, but that radians is that pure unit, so we don't really have to worry about that. This is feet, and that's per second, so my units for this one is going to be feet per second. I know it's weird to kind of cancel out that radians, but you can just ignore it when you're not talking about angular velocity. Once you shift over to linear velocity, now you've got miles per hour, or feet per second, or meters per second, or centimeters per hour, or whatever it is. So that's my linear velocity. We also have to find our distance traveled in 10 seconds. We only have one equation that involves distance, so we're going to use our linear velocity, which we now know. So I'll get that over here. So this is our formula that we're going to be using right now for find our distance. Our linear velocity is the 5 pi over 9. Our distance is unknown, but I do know my time is 10. And so now I'm solving this formula for d. So I'd multiply both sides by 10. These cancel. So I'm left with 10 times 5 is 50 pi over 9, and my units for this, some distance, is going to be in feet. And you can leave pi in your answer. That's totally fine. Sometimes they ask you to like round it out, find the nearest tenth or hundredth or whatever, but I'll always accept it in terms of pi. So that one you had to use like 2 of those formulas. Same kind of idea for this one. So for our last 2, we have a radius, and it's telling us we move 80 revolutions per minute. And we're finding the angular velocity and the linear velocity. So our angular velocity, remember, is given by this formula of theta over time. And our linear velocity is given by those 2 formulas. So we're going to figure out which one we're going to use here in a second. If we're given our, so right now we're not given our angular velocity because it's always in terms of radians per minute. But they do give us like 80 revolutions per minute. So let's see if we can manipulate that in terms of time. This would be like per 1 minute. So our time is going to be like 1 minute. And we got to figure out like what 80 revolutions would be on a unit circle in terms of an angle. So we know 1 revolution, just like 1 orbit, is equal to 2 pi. So if I am looking for 80 revolutions, that would be 80 times 2 pi, which would be 160 pi. So that would be what my theta is actually represented as 160 pi, and then this would be per minute, so per 1 minute. And that would be my like angular change, which is my theta value over my time. So 160 pi radians per minute. So we didn't really have to do too much to this one. It's not like you have to really show all that work anyway. That allows us to find then, like, manipulate this because it looks awfully similar to our angular velocity, but it's not in radians per minute, it's in revolutions. So we have to multiply by that factor of 2 pi, and then we will get our angular velocity. For our linear velocity, we have 2 different formulas. We got our distance over time and our radius times our angular velocity. Well, since this one already gives us a radius and it already gives us a angular velocity, or we just found it, so we can use that formula of our radius times our angular velocity. Our radius is 6. Our angular velocity is 160 pi. And if we do 6 times 160, we get 960 pi. And our units on this are like our linear velocities, miles per hour, or whatever it is. So ours is feet per minute. Okay. Last one. We are finding the angular velocity, linear velocity, and distance. So I'm looking for this unknown, I'm looking for a v, and I'm also looking for the distance, and this is traveling in 15 hours. So my time for this part at least the distance section is going to be 15 hours. It tells us that we have feet, and it tells us this orbit in 6 hours, 1 orbit in 6 hours. So if I'm finding my my angular velocity, it's a lot like this one, where this 6 hours is going to be the time as far as my linear or angular velocity is concerned. This 15 hours here really only goes along with the distance traveled in 15 hours, so don't let that confuse us. It's like a different setup to that problem. But to start with, we're going to look at our angular velocity of some change in theta value over our change in time. We've already talked about this orbit. So an orbit is all the way around my circle. So that means that my theta value, 1 orbit, is going to be 2 pi. And I'm changing that 2 pi in 6 hours, which means that I'm looking at an angular velocity of pi over 3 radians per hour. Okay, so that's one thing. So I'll write that over here because I might need it. My linear velocity, I could use distance versus time, but I don't know my distance. I do know some time, and this time really too, but that doesn't really help me. But I do know a radius, so I can use this formula, r times my angular velocity. My radius is 5 feet. My angular velocity just found was pi over 3. So I can write that as 5 pi over 3. And then remember, linear velocity is like miles per hour. So ours would be feet per hour. So far we have two of the things that we have accomplished or found. We have our angular velocity, we have our linear velocity. Now all we need is distance. We've already done something like this. Distance is only in one of our equations. It deals with this one. So I'm going to start there. It's a good bet. So I'm starting there. I know my linear velocity is 5 pi over 3 because I just found that. I don't know my distance. And then I'm looking for the distance traveled in 15 hours. So that's going to be the time that I use. So in order to solve for our d value, our distance, we would multiply both sides by 15. This will reduce, or you can kind of multiply it out and then divide. 15 divided by 3 is going to be 5, so I'll have 5 times 5, which will be 25 pi. And this distance is in terms of some, amount that I'm leaving, or some length, which is our value is in terms of feet. So our distance is 25 pi feet. Feet per hour, radians per hour. Okay. So most of what this back page is, again, is just like a manipulation of the formulas. And if you have the formulas, I'm hoping that, because you will be getting the formulas, I'm hoping that like you can manipulate those in a way that will make a little bit more sense. Again, my suggestion to you, if you are getting a little confused on what to use, is I always like write down everything that I have or everything that I want, and then I see which those, or what those variables are in, which formulas. So then I can at least have a starting point to see if I can manipulate things in a certain way. Like I said, this is probably the hardest section, especially because like this seems a little bit disconnected, the domain part. And then we have like that second section of velocity, but this is where like this velocity section tends to be kind of confusing for some people. So hopefully like the practice tomorrow will help iron out some of those kinks.